first we'll plot load line for BJT. This is the basic transistor circuit. The symbol used in the circuit, this one, is the symbol of NPN transistor, and the symbol used, this symbol is used for PNP transistor. Now in this circuit we will mark all the transistor currents, that is base current, collector current and emitter current. Now if we apply KVL in this loop, collector emitter loop, here we have this battery VCC, it can be replaced with the battery and the other terminal can be grounded. Now in this circuit, this battery VCC and VBB, resistance RC and RB, are the components used to bias the transistor. Biasing means transistor, to make the transistor to operate either in active or saturation or in cutoff. So these four components will be used to bias the transistor. Now if we apply KVL in this collector emitter loop from ground to ground, first we will mark all the polarities. IC is flowing downward, so the polarity of voltage across RC will be like this. VC polarity already marked. Now we will apply KVL in collector emitter loop. We get VCC minus VCC plus IC into RC plus VC equal to 0. Now IC is equal to VCC minus VC upon RC. It can be modified as IC equal to minus VC upon RC plus VCC upon RC. Now this equation can be seen as equation of straight line where y equal to mx plus c. Here m is equal to minus 1 by RC, y equal to IC and x equal to VCE, and c, that is intercept on y-axis, is VCC upon RC. Now as this is the equation for straight line, if we plot this straight line, we get a graph like this. From this slope it is clear that the line is a decreasing straight line. Negative slope means decreasing straight line, and this line will be like this. In this line the slope is minus 1 by RC, y-axis is IC, x-axis is VC, and intercept on y-axis is VCC upon RC. Now if we put this equation of IC is equal to VCE minus VCE upon RC plus VCC upon RC. If we put IC equal to 0, this point can be obtained. If we put IC equal to 0, VC upon RC will be equal to VCC upon RC, so VC will be equal to VCC. Now this is the load line of PGT, or specifically DC load line. Now in this uh, transistor circuit, if we select any particular value of IC, suppose we have selected any particular value of IC, this is IC, then corresponding value of VC can be obtained by plotting this load line. This value of IC is called ICQ, and this corresponding value of VC is called VCQ, and this point is called Q point, whose coordinates are IC, VCEQ. So this is the operating point. If operating point lies in this region, then we can say that transistor is biased in active region. If Q point lies in this region, then transistor is biased in saturation. And if Q point lies in this part of the load line, then transistor is said to be biased in cutoff region. So this was the load line. Now once the Q point of the transistor is fixed, means IC and VCE values are fixed, then it is expected that during operation these two values should not change. If these values changes, Q point shifts on the load line. If Q point goes beyond active, it will transistor will go in saturation, or it may go in cutoff. Normally it happens if surrounding temperature increases, the collector current IC increases, and due to increase in collector current IC, the load line the operating point Q shifts upward on the load line, so transistor may enter into saturation. Now we'll see the parameters which affects the load line of the transistor. There are three parameters. First is VBE, base to emitter voltage. VBE decreases by approximately 2.5 millivolt for 1 degree rise in temperature. If temperature rises by 1 degrees, then VBE decreases by 2.5 millivolt. If VBE decreases, then it causes IC to increase. We'll see how IC increases due to decrease in VBE. Now in this circuit, if we apply KVL in this loop, this is base to emitter voltage VBE. We'll see all these voltages and currents when we start DC analysis of the transistor. Now if we apply KVL in this loop, base emitter loop, we get equation minus VBB plus IB into RB plus VBE equal to 0. Now IB is equal to VBB minus VBE divided by RB. Now here we can see that IB is inversely proportional to VB, because if VB increases, as it is with negative sign, so with increase in VB, IB decreases. Now if VB decreases, IB increases, and we know that if IB increases, collector current IC increases according to the equation IC is equal to beta into IB plus 1 plus beta into ICO. So collector current IC will increase, and this increase in IC will shift the operating point of the transistor. Now the second parameter is collector reverse saturation current ICO. This collector reverse saturation current increases by approximately 7% for 1 degrees rise in temperature. If temperature rises by 10 degrees Celsius, ICO doubles. Means ICO at any temperature T2 is equal to ICO at any temperature T1 into 2 raised to power T2 minus T1 divided by 10. According to this formula, if we put here the value of IC not at any temperature at any another temperature, it can be calculated using this equation. And we know that if temperature rises by 10 degrees Celsius, ICO doubles itself. So with increase in temperature, ICO increases. We know that the equation IC is equal to beta into IB plus 1 plus beta into ICO or ICBO. This ICO increase will increase the collector current IC, and if collector current IC increases, again the load line, the operating point will be shifted. Now the third parameter is beta, current gain of common emitter transistor. This beta increases with temperature. Beta increases with temperature. Also beta affected due to a replacement of transistor. If we replace a transistor, beta is affected. So beta is affected due to replacement of transistor. Now we have this equation IC is equal to beta into IB plus 1 plus beta into ICO. If beta changes, then IC obviously changes. If IC changes, the operating point is shifted on the load line. Now we'll see biasing circuits of transistor. Biasing circuits of BJT. First is fixed bias circuit. In fixed bias circuit is very much simple. This is a fixed bias circuit. In this fixed bias circuit, the stability of the circuit against temperature is very low. Means if temperature changes, the collector current IC will necessarily be increased, and it affects the operating point of the circuit. Second one is collector to base bias circuit. In collector to base bias circuit, there is little difference in the circuit. The biasing is provided through collector, and the third circuit which is very important, is self bias circuit. In self bias circuit, we'll have this emitter resistance Re, and rest of the circuit will be similar to fixed bias circuit. Now in this circuit we have one advantage. If you mark the currents IC, IE, now as if you apply KVL in this base emitter loop, before applying KVL we will replace this VCC with a battery. Now we'll start the analysis. If we apply KVL in this base emitter loop from ground to ground, in this base emitter loop, we have this equation minus VCC plus IB into RB plus VBE, and for this voltage drop across RE we write VE plus VE equal to 0. Now equation for IB is equal to VCC minus VBE minus VE divided by RB. Now earlier we have seen that three parameters beta, ICO and VB, all the three parameters tend to increase the collector reverse saturation, collector current IC of the transistor. If collector current IC is increased, the transistor may burn or the operating point will be shifted. Now in this equation we have this VE term, additional term, and we know that it is with the negative sign. If VE increases then IB decreases. So here if these three terms increases, then surely the collector current IC increases. First temperature is increased, these three parameters increases and IC increases. If IC increases, then we know that IC is equal to IE equal to IC plus IP. IC increases, so IE increases. IC increases, IE increases. If IE increases, we know that IE, the drop VE is the voltage drop across RE, that is IE into RE. So VE equal to IE into RE. This voltage increases. If this voltage increases, then from this equation we can see that with increase in VB, VE, IB increases, IB decreases. If IB decreases, IC is equal to beta into IB plus 1 plus beta into ICO. If IB decreases, then IC again decreases. So this circuit is providing compensation of itself. So this circuit is called self bias circuit, and this resistance Re is providing stability to the circuit against a temperature. So this resistance Re is called negative feedback element. Negative feedback element. Now we'll see operating modes of the transistor. Operating modes are decided by looking at the input and output terminals. Up to now we have shown only biasing. Now I will show the input and output terminals of a BJT. We will see one example and then we'll see the operating modes of BJT. Here we have a transistor circuit and we have provided biasing. In this circuit we have not shown, still we have not shown any input terminal and output terminal. The voltages that are applied are called biasing voltages, and for deciding the operating mode we should know the input and output terminal. If we apply a voltage here for amplification, then if we take output at this terminal, then now we can say that this collector terminal is output terminal, this base terminal is input terminal of the BJT, and emitter is common between base and collector terminal, so it is called common emitter mode. In this way we will define all the operating modes of BJT. Now the first operating mode is common base. Common base mode. Now in I will not show any biasing here. If we apply input at this terminal and output across these two terminals, it is emitter terminal, it is base terminal, it is collector terminal, it is base terminal. Now in this BJT we have input between emitter and base, output between collector and base. This is called common emitter mode. Now at the input terminal we have the current IE, and at the output terminal we have current IC. So for common base transistor we will define its current gain. Its current gain is defined as alpha, which is equal to the ratio of output current by input current. We know that IC is nearly equal to IE. IC is nearly equal to IE, but IC can never be greater than IE. So IC will always be less than IE. Now we can say that alpha is nearly equal to 1, but never less than 1, never equal to 1. Always less than 1. Second is common emitter mode. Now in this transistor circuit we have applied this time input between base and emitter, output between collector and terminal. This is called common emitter mode. In this common emitter mode, the input current will be base current, output current will be collector current. Now if we define the current gain, this will be equal to output current IC by input current IB, which is also called as beta. And we know that IC is very greater than IB. If IC is very greater than IB, beta will be very greater than 1. Typically beta is around 50. Third is common collector mode. Common collector mode. Here we are applying the signal, input signal between base and collector, and outputs is taken between collector and emitter. This is input voltage and this is output. The current in the input terminal is base current and output current is emitter current. The current gain of a common emitter, common collector mode or common collector transistor is defined as gamma, which is equal to output current IE by input current IB, that is base current IB. So these are the three modes of operation of the transistor BJT. Now, as we have already seen the symbols of the transistor, this is the symbol for NPN transistor. In this NPN transistor, this is collector, which is N region, this is base, which is P region, and this is emitter, which is N region. Here this is collector, which is P region, base, which is N region, and this emitter, which is P region. This is PNP transistor. The actual direction of currents in these three terminals is shown in the circuit, and here the actual direction of currents will be reverse. The arrow shown at the emitter terminal shows the uh, direction of emitter current when base emitter junction is forward biased. Now the terminal voltages for PNP transistor, the terminal voltage is like this, and this will be the last terminal voltage, that is VEC. For this NPN transistor, the terminal voltages will be VBE, VCB and VCE. These are three voltages of the transistor, and one thing will be true for this transistor, that VC will be equal to VCB plus VCE, and also IC will be equal to IE will be equal to IC plus IP. These two statements can be obtained by applying KCL and KVL. This statement can be obtained by applying KVL, and by applying KCL this statement is obtained.